Our last for the review week, the 2 lectures make sense because once I get a copy of the final exam, it's necessary to run maybe 2 sessions of reviews, right? But next Monday, I don't know what to cover over there. Would you like me to run some examples or want to go leave for your Thanksgiving break earlier? Do other professors, do they still have lectures on Monday or no? They do? No? Yeah? Wednesday? Wednesday's the break, right? Okay, but Monday's not. Okay. So still have to teach on Monday. Would you like me to cover something on Monday? More examples, or you are good? I don't have the final exam copy yet. That's a problem. If I have it, I'll run final reviews. I probably will request the final exam, some of the practice exams from Dr. Morris from the past few years. Right. Cool. So today we have the homework 10 due, right? So there's one last problem I want to cover. Let's take a quick look at it. Why it's so dark? Where the switches are? Not these ones. Okay. If you have a copy of the homework 10 problems, I think it's 10.41. We went through this briefly, but I think I probably need to talk about this a little bit more today. This is still today. .41. It doesn't have a schematic with it. It's only like showing 2 ports. A, B, VAB. Here's a circuit, and that's the output. So it's asking, what is given here is, so when there's no external load, it's connected to the terminal A and B. When there's no external load, the voltage here is 360 degrees and 360 volts and 0 degrees, and that's the RMS voltage. What is this telling you? When there's no load, is that familiar to you? So no load, we measure the output. What is this? Yeah, the 7 is equivalent voltage, right? So they're telling you when there's no load. Remember when we are trying to find out the 7 is equivalent voltage, we remove the load and find out the terminal voltage. Then that voltage is 7 is equivalent voltage, right? Same thing. It's telling you there's no load and voltage measure here is 360 volts and 0 degrees RMS voltage. So in that case, if you convert it to the 7 is equivalent, you are getting this. Okay, because we are doing that equivalent circuit, so I'm assuming that there will be a ZTH here as well. And these are the 2 terminals, A and B. So this is from the first given condition, so we can find out this type of circuit. Okay, see the next. If there's a load which is 100 ohms connect to the terminal, and you measure this again, it's giving you 180 minus J 60 volts RMS. What is this telling you? Or what you can find out by these two conditions? Seems like we are trying to find out the Thevenin's equivalent circuit, right? But now we already have that VTH, but we don't know the ZTH. That's a problem. So how to find the ZTH? Now it's given that for this kind of circuit, someone is trying to test it, right? Connect a little resistor to the output and probe the voltage. Since you don't know anything about the black box inside, right? You connect the resistor and you probe the voltage here, becomes this much. So what you can get from this? The current, yes. Because you know the voltage here, you know the resistance, so you can find out the current. Current is what? 180 minus J 60 volts divided by 100 ohms. That's a complex current, right? So this is 1.8 minus 0.6 J, right? Amps, RMS. Okay? What else you can find out here? So current is calculated, voltage is given, and you know the voltage drop across the ZTH. So you can find out the voltage drop, and you know the current, so you can find out ZTH easily, right? So ZTH will be what? 360, 0 degrees minus 180 plus J 60 volts divided by the current. Okay, so you can find out ZTH. Let's calculate it. 360, it just only has real part of it. Let me see how I did it. Did I use angles or did I use complex numbers? Let's try one of them and see if that works, okay? So I think I usually prefer phasors. How would you like to proceed? We can take out one. This can be simplified a little bit, right? So this becomes 180 plus J60, right? Can we simplify anything from here, or no? It seems to be unnecessary, but we can do this, right? 100. Okay, times 1.8 plus 0.6 J for both top and bottom. So this is giving us to calculate it, right? 1.8 squared plus let's calculate it. Let's do minus first. Minus 0.36, which is this guy's square, plus and times 2. Let me know if this is wrong. So this is 1.8 square plus 0.36. Did I calculate it wrong somewhere? I think that's right. Okay, so let's calculate 1.8 times 1.8. Okay? 80 plus 60J. Which is what? It's been a while. Forgot what is this. ZTH, right? So we're calculating ZTH. So ZTH. So the circuit becomes this. So this impedance is 80 plus 60J. So this is the equivalent circuit here. Okay, is this going to be useful? It's going to be useful. Let's look at it. So first, find impedance. So this is part A. This is part A, okay? Find the impedance that should be connected across A and B for maximum average power transfer. So connect the impedance here to achieve maximum power, real power transfer. So like what I said last time, for the circuits only have linear components. Remember in the past, we derived the maximum power transfer, right? I have a resistor here, and you want this RL equals RTH in order to have a P max, right? P max transfer to the load. I think we derived it in one of the lectures. Look at the notes from the previously. So for here, how do we achieve a maximum real power transfer to the load though? Remember the power, right? If you have a reactive power, it's getting stored and then sent back to the source eventually. So it's not being used. So in order to achieve maximum real power transfer, you need to make the impedance value should be a conjugate of this ZTH impedance value. So you can get that reactive part cancelled, but I only have the real part matching to whatever the ZTH has. So in that case, the load should be what? Definitely 80, right? Minus 60J. So in that case, the overall impedance, if you're looking from the source, it's getting canceled. There's no reactive power eventually. Okay, so you can also say this is getting corrected. Sometimes it's called power correction, because it's not wasting the source power or the source capability, whatever, the driving capability to send something to a reactive part of the circuit, and it's getting stored and sent back later. You don't need to do that. So it's eventually just a real power consumption, eventually. Okay? So in that case, you can achieve maximum real power delivered to the load. So in that case, the next question is asking you the maximum average power transfer to the load from part A. How to calculate that? So yes, this load is achieving maximum power transfer, Pmax. But what is it? How much is it? So these are RMS values, remember? This was labeled or given by the problem, okay? We have done this for several times. Remember, we have two different methods, right, to calculate real power. What are the two methods? You can either focus on the component, the resistor, right, the real part of the components, or you can focus on the whole impedance. But eventually, you convert. Remember the P, which is the average power, equals what? Vm, Im, which is the peak voltage and currents, divided by 2, times cosine this minus this. If you focus on the resistor itself, there's no phase shift, so this is 0 degrees. So this becomes 1. So you just focus on the resistor, look at the resistor, just resistor itself, okay? Find out the voltage and find out the current, and there shouldn't be any phase shift. Remember? The resistor's voltage and current, just looking at the resistor itself, there's no phase shift. Why? Because V divided by R equals what? VR. Is there a phase shift? No. Okay? V and I doesn't have a phase shift for resistors. Okay? So if you just focus on the resistor, it's asking for average power transfer to the load, right? So only look at the load. Only look at the load. If you have this kind of circuit, only look at the load. What is it? What's the average power consumed by the load? It's only the 80 ohms, right? It's only the 80 ohms. This minus 60J is not consuming real power. It's basically only the 80 ohms consuming the real power. If you only look at this, you can actually imagine this impedance is basically a what? Resistor and what? Capacitor, yes. Why? Remember, capacitor equals minus J over omega C. Okay? Inductor's impedance cannot be negative. So it has to be a capacitor. So you have R and minus J omega C. Now you don't care about it, do you? You don't care about it, right? It's gonna be the same thing. It's gonna be the same. You don't care about this guy since you only look at the resistor. Focus on the resistor. Focus on the resistor. Okay? So now let's find out what's the voltage across it. What's the voltage across it? There are two ways to calculate this, right? Two ways to. So what's the easiest way actually? Before we focus on the resistor itself, what's the easiest way? Yeah, we can actually, it's basically just a voltage divider, right? So the VRMS is over here, just look at the, can we do that? Let's come back later, okay? Let's follow the traditional way, make sure we're not making any mistakes. Okay, so find out the voltage first. What's the voltage? VRMS voltage. You know the overall voltage now, right? What's the VRMS voltage across this guy? How do we calculate it? Think about it before we move forward. This is the overall voltage with the phase, right? You could definitely use the voltage divider to find out the voltage across it. But eventually things will be cancelled. How do we do it? We can find the current first, right? Yeah. Current equals 360, 0 degrees divided by what? Yeah, 160. These two are cancelled, right? It's the impedance. Yeah, so it's basically only a real part. There's no reactive components. The impedance is 160 ohms. So that's the current with the phase actually, but it's 0 degrees, right? So that's the current. And this is RMS because 360 is RMS. So this is also RMS. Okay? You know, P also equals RMS squared times R. Okay? So after you get RMS, just RMS squared times 80, done. Or if you want to use voltage, which is also fine, I RMS times R times the voltage resistor, so the current flows through it, times the resistance. You're getting the voltage drop across it, and then divided by what? This is what? This is voltage, right? So voltage squared divided by R is also the power. But basically it's the same stuff eventually. So if you this could be a shortcut, okay? So in the future, if you are able to find out IRMS easily, so just directly use IRMS squared times R to find out the real power. This is one of the easiest way to find it. But sometimes I is not that easy to find, depending on the impedance, right? This time it's super simple because eventually adding together is just giving you a real number, right? It's super easy to find out, but sometimes it's not that easy. But for this case, just directly use RMS squared times R. Will give you that power, maximum average power transferred to the load. And there's the part C as well. It's giving you several options and asking you to form a load like this. It's like a scenario in the real world is this circuit's given, right? Circuit's given, and the lab manager tells you that there are these components in the drawer in the lab available for you guys. Okay, just form a load to achieve maximum power transfer to the load. Okay, that's a real world problem here. So what are the components available? It's like these ones. Oh, numbers and components. So you have to form a impedance of 80 minus 60J, right? Okay, so you know it's a capacitance. So it has to be capacitors. So let's form a 80 ohms first. 33 and 47 is like a first degree math. What are the numbers can form an 80? Okay, so 33 and 47 is forming an 80 ohms, right? And then for the negative 60J, you just have to use omega, the frequency, plug in, and do the calculations like this. So this is minus J omega C equals what? Minus 60J, right? Cancelled. So you can calculate back to get C. Okay, so what is C? So for my numbers, I think my C is, oh, I didn't write it down here. Do I have it? I don't have it, but for example, okay, 44 microfarads, for example. Okay, this one. Okay, and it gives you 22 microfarads caps in the lab. How do you form this capacitor? Just got two in parallel. Yeah, that's how you want to work. How you want to do it. Very simple. Very simple. Okay. All right. That's everything about homework 10. I think we did it for 3 lectures. So luxury compared to the earlier time of the semester. Haven't done this in the past. Always rushing. For homework 11, it's 3-phase voltages. So I think before we get into the problems, I need to introduce the concepts first. So it's actually very simple. there's only one circuit model that you need to know, and that applies to all the problems in the homework assignments. So basically, this is what the tutorial want to teach you actually. So three-phase is basically just the three AC waves, AC sinusoidal voltages, power voltages, and it's able to deliver voltages. Oh, they have a common ground. So circuit is drawn in a very weird way, but you need to know that usually in the past we drew a power source like this, right? And we ground it. But they didn't show you this is ground, but this is a reference voltage. You can treat this point as ground. And these three are three terminals. You can treat it like this, plus minus, plus minus. It's AC wave. It's always oscillating, so it doesn't matter which is plus, which is minus. But you want to know that plus minus, that polarity shows you a phase, a certain phase difference. So this plus minus defines the phase. You got one. This is impedance, and more impedance, and even more impedance. Okay? And that's it. Pretty simple. So what are the impedances? So these are, so it draws three lines over here. So these are the source impedance. So it's extracting the impedance the source into the circuit, but actually it's just a model. It's not a real impedance over there. It's modeling the source impedance. So it draws it here. Okay, it's just a model. So this is the line impedance. Transmission lines, the wires, the lines, they have impedance. Could be wires, capacitor impedance, inductive impedance as well. Because none of the conductors are ideal, right? Okay, so it's a line impedance, and this is the load impedance. So the load is also in three phase. That's the most important part, because this is whatever is connected to the three phases of the voltage. So this part, which is ground, the reference point of the load, is usually shorted to the source ground, so they are having the common reference, common ground. Okay? That's it. This is the most complicated circuit you can see. However, sometimes they assume that there's no source impedance, or there's no line impedance, or there's no line and source impedance. So I'm going to tell you which problem is assuming that. I didn't tell you. It didn't tell you in the problem, but I'm going to show you which one, okay? But for a complete version of the model, it looks like this. You got three different phases of the voltage as a power supply to supply to the three-phase load. So one of the applications I showed you guys, right? Let's take a look at it. One of the applications of the three-phase voltage is an inductive motor. Do I still have it here? I have it here. I have it here. Notes. Three-phase. Okay, take a look. Take a look. So that's the three-phase of the voltage from the source, right? And you can see the three phases are connected to three different. It's a stator. What is a stator? Let me show you. Here's a stator, right? Magnets, metal bars with a coil around it. So it's going to generate a magnetic field, which is able to induce a current in the rotor, and which creating opposing magnetic field, so which is able to, so the stator is able to pull that rotor away from its magnetic field. So in that case, it's able to do it. So for example, the rotor is getting pushed. So the rotor is being pushed away by this stator whenever its phase arrives, right? So it's being pushed to this one, and the second one's phase will arrive as well, and then we'll push it to the third one. So it's relaying that kind of force to spin the rotor inside. So it's more efficient because it's always having something taking over, and so it won't stuck. So there are some two-phase inductive motors as well, but it won't be as efficient as the three-phase motors. That's one thing you need to know. Another thing is this is a internal view of that motor. You can see it's a rotor, it's a stator, right? And another reason we want to use three phases is because as a common application, everyone should know this. I showed you the first time I covered three phases, but still want to let you guys take a look at it, right? So a very common application, you have your adapters. The adapter for the phone, smartphone, or for your laptop. This little black box is a little transformer. So that transformer converts, it step down your AC voltage from the wall, like 120 volts AC, to a lower voltage, could be 20 or 25 AC oscillation, and that AC oscillation will arrive this rectifier. If you take microelectronics, you'll learn diodes. So the rectifier is able to remove that AC oscillation and convert it to a DC. But the DC won't be perfect. You see there's a little ripple, there's a little dip and bump. But that's okay, since you can further filter out these little ripples and give you a pretty steady DC voltage to supply that DC power to your laptop or to your smartphone. Usually the smartphone is getting 5 volts and laptop is getting 20 volts DC, pure DC. Okay? But this is a very common circuit. It's just everywhere in your real life. It's everywhere. So remember that AC voltage comes in. First, you need a transformer. So transformer will step it down to a lower voltage, and then you use that lower voltage, goes through a rectifier. A rectifier will convert that AC oscillation or AC voltage to a DC voltage, and DC voltage goes through this low pass filter over here. It will remove the ripples and give you a really stable DC power supply. Okay, that's how that works. So if you have, let me come back here. Zoom in. If you have three phases, you just have more peaks, so it's just more efficient. Okay, so that's the whole point of using three phase. Usually, three phase voltages are being used for factories or some power hungry factories or appliance. But usually, your fridge at home and computer desktop towers, they don't need the three phase voltages. It's always single phase. Okay, to power up regular appliance in the house. Okay, that's the overview of that concept. And so for the first many pages of the homework 11, it's really simple because it's just testing you that concept. Okay, so the three phase voltage, they are being split or being separated into three phases. It could be, for example, phase A, phase B, and phase C, like this. This is a standard way to do it. 0 degrees, negative 120 degrees, and 120 degrees. So are splitting that 360 degrees into three different phases. So it could be 120 degrees apart from each other. And if ABC follows the order clockwise, so it's called a positive phase sequence. Positive phase sequence. Okay, ABC. It doesn't matter. It's a 0, a negative 120 or 120. It could be this. Okay, A is here. If A is here, B will be here, right? It's also clockwise. As long as you are having 120 degrees in between each other, you'll be fine. So this is also called positive phase sequence. All right? But if you have a case like this, A, B, C like this, it's counterclockwise, right? Counterclockwise. This is called negative phase sequence. Okay, it doesn't have to start from 0. It could start from somewhere else as well. As long as it's having 120 degrees in between all the 3 phases, it will be fine, okay? So what if it doesn't have 120 degrees in between the 3 phases? So a balanced 3-phase system requires the following features. So we'll know whenever it satisfies an unbalanced system. So balanced system has 120 degrees differences. Phase differences. Okay, and same omega, same frequency, and same amplitude. Sometimes they say magnitude, it's the same thing, magnitude. Okay, let's take a look at some examples over here. This one. So all of them are cosines, right? So it's pretty simple. Phase A is 0 degrees. It's a very standard one. So A is over here. B, negative 120 degrees over here. C is positive 120 degrees. Okay? So it's going to be ABC. ABC like this. It's clockwise. Is this positive or negative sequence? Positive sequence because it's clockwise, right? Okay, is balanced or unbalanced? Same amplitude, same frequency, and 120 degrees in between. It's balanced. Okay, what about the next? This one. So all sines, right? You have to convert it to cosines first. So what are the cosine values? So sine theta equals what? Cosine theta minus 90 degrees, right? Always do this first. So convert all these angles to this, theta minus 90 degrees first. I will find out it's ABC. It's going to be counterclockwise in that case. But could you tell before we do a subtraction here? Because it's the same thing, right? Subtract the same values, is still the same differences, right? So look at the angles. I drew it as 0, but actually it's not. It should be cosines. Here, should be here, right? But doesn't matter. Let's just take a look at it. So for this one, for example, it's 0 degrees. Okay? And this is negative 240 degrees. Will be this guy, right? Negative 240 degrees, right? And this one is positive 240 degrees, which is this guy. So it's going to be ABC. It becomes counterclockwise. Just a negative sequence, right? It's a negative sequence. And is this balanced? Yes, it's 120 degrees in between, and same frequency, same magnitude. Okay? So see which option you want to choose. It's balanced, definitely. It's going to be one of these two. And it's negative, right? So it should be A, right? Okay? How about this one? This one. I'll let you run it. So yeah, because they are not all cosines or all sines, so I have to convert it to cosines first. So this is negative 90 degrees, and this is 240 divided by minus 90 will give you 150 degrees, right? So it's negative 90 degrees, which is A, and positive 150 degrees over here is B, and 30 degrees over here, which is C. Okay, so negative 90 to 150. How much is it? So B is 150 over here, right? So we're getting 30 degrees left. So 30 plus 90 is 120 degrees actually, right? Because this guy B is 150 degrees, right? So 150 degrees. So we have 30 degrees left because totally you are getting 180, right? So 30 degrees left, and this is a right angle. So 120 here, 120 here. And C is getting 30 degrees. Overall, you have 150 minus 30. So this angle is also 120. Okay, you got two 120s. This must be 120 as well. So it's balanced. Okay, it's balanced. So it has to be one of these two. Is it negative or positive? A, B, C. It's clockwise. It's positive, right? Okay, so it's going to be balanced and positive phase sequence. All right. What about next? I'll run this one as the last one because it's all super simple. It's all very similar. So this one, convert to cosine first. This is giving you negative 30 degrees. And minus 90 degrees is going to give you 90 degrees. And just keep the same, right? So we're getting A, B, C. A is, this is 30 degrees. B is 90, so it's giving you 120 totally, in total. And C is negative 150, so you are getting 30 degrees left. And plus the right angle is getting 120 degrees as well. So it's balanced. It's balanced. And you can find out the same frequency and same magnitude. It's balanced and A, B, C like that, counterclockwise. It's negative, right? It's balanced and negative phase sequence. It's going to be A, right? Okay. Seems like everything's balanced. All right. Let's look at this problem. Look at this circuit. Scary, right? What? Seriously? It's actually really simple. Remember the model I drew at the very beginning of the class? Could you tell anything here? What is it? 1, 2, 3, 3 faces. Common ground. What is this wire doing? Shorting the grounds, right? The load, the ground of the load to the ground of the source. So they have the same reference. Okay? So what are these? Source, line, and load. So after you know that, it becomes super simple, right? That's a source impedance. It's extracting that source impedance from the source, so this source becomes the ideal source, no resistance or impedance inside. It's just extracting whatever in the source, okay? It's modeling that kind of impedance of the source. This is the line impedance. It's a very long transmission line to deliver power, so it's a long line impedance. This is the load impedance. This is what is really being driven by the circuit. Sometimes it's ask you the terminal voltage. So here's the terminal, actually. It's called the terminal. This is called a terminal because the terminal is two terminals connecting to the load, right? So you get a load. This is whatever, could be an inductive motor or something. So eventually you connect it to the line, so you can get everything powered up, right? So let's see if we can. We still have 6 minutes, so you can calculate one parameter, for example. So it's asking for current, I/O, which is current from here to here. We can treat it as a common ground, but actually it's anyway, it's a zero eventually. But it's asking you to calculate the current. It's just trying to let you practice the complex power calculations. Okay, how do we calculate the current in here? So this line is the main. This is the main line, right? It's like a hub, because it's basically like you have three phases, right? Three phases of power, and you got three phases of load. And eventually, all this current merges to one node and comes back to the source reference point. How do we calculate it? KCL, yes. Okay. It's because the voltage here is given, I think. Let's see. So what is given is, so these are all the same VMs. Remember, you need a balanced three-phase voltage source system, right? So which means all the VMs are the same, but I only have 120 degrees difference. Okay? So 0, 120, a negative 120. But the VM is the same, which is 240 volts. Okay? So what you want to do is just treat this point as ground, and use this voltage divided by the complex number, the impedance over here, to find out the current. How to do that? 240 volts, 0 degrees, divided by what? Just add them together, you find out they're all the same. It makes sense, right? Just transmission line should be the same. If it's not, probably you want to fire some of the power electronics engineers who connect a different transmission line over there. So add them together. So 0.2, 0.8. So that's 1 plus 79 is going to be, it's going to give you 80. It's 80, right? And for the inductive part, it's 1.6, 0.4 is 5, and 60. So it's plus J60. Okay? So that's the A phase. It's called A phase. The first phase. This one has 0 degrees. But for the second phase, you have to plug in 120 in there for the calculation. Okay? But for phase A, or A phase, you just directly use 240 and 0 degrees and divided by the impedance. So it's giving you IA. Okay? Calculate it. Do the same thing for IB, similar thing to IB and IC. And then eventually, these will be 3 complex numbers, and IO for the first equation is, for the first question is IA plus IB plus IC. You can use the phasor math calculator that I showed you on my website for the calculation. So you have the magnitude and angles, and just directly adding them together. You find out the final result has a super small angle, so you can ignore it because it's not perfectly 0. It's like a negative. No, it's 0.5 times 10 to the negative like 50's power. So it's basically just 0, right? So again, if you get that value in the calculator, just directly use 0 instead of a very small number. So eventually this should be 0, okay? But you want to verify it, see if that's true. Okay? And there's a part B. It's asking for VAN. Okay? Getting a little bit familiar for the terms. So remember, for all the circuits covered in this chapter, it's assuming that this is phase A, this is phase B, this is phase C. Okay? And for the terminal, it's being labeled as capital A, capital B, capital C for these terminals. And for this terminal, it's labeled as N. It's like negative or something like that. It's basically just ground. Okay? So asking for voltage of VAN. See VAN here. Is that easy to do or no? Yeah, just voltage drop, right? You got this complex resistance, and you already calculate the A current, phase A current. You just did it. Just IA times the impedance. So you can find out VAN, right? So the voltage drop between A and N. Okay? So what about VAB? VAB. Yeah. So it's gonna be VAN minus V what? BN is VAB. Why? Because VAN is what? VA minus VN, right? VBN is what? VB minus VN. Okay? So you can calculate VAB easily by doing this. So this covers part ABC. And for part D, we'll talk about it on Friday. and then cover the rest of the problems on homework 11. Okay? We'll see you on Friday.